Then 33, a cubical box, 1.8 meters on its edge, has its base horizontal and is half filled with water. The remainder of the box is filled with air under a gauge pressure of 69 kilopascals. One of the vertical sides is hinged at the top and is free to swing inward. To what depth can the top of this box be submerged in an open body of fresh water without allowing any water to enter? So this is the situation. It is half filled with water, so half of 1.8 is zero point 0.9. The box is cubical, so this is 1.8 perpendicular to the screen, 1.8 meters also. And the remainder is filled with air under a gauge pressure of 69 kilopascals. So let's draw the pressure diagram then. Because this box is free to swing inward but cannot swing outward, the only way it can swing inward is to submerge the top so that there will be pressure on the outside surface to push the one vertical side inward. So there's a possibility that will open. And when that happens, there will be no more reaction here on the bottom. So this is the liquid surface. This is the question H. This is the pressure diagram for the inner face of the vertical side. So 69 kilopascals. Then let's compute for P1. P1 is specific weight of water times depth 0.9. And there are only two forces that push the inner vertical face outward due to this rectangular pressure diagram and this triangular pressure diagram. Now, when this is submerged, there is also a force that pushes the side inward, and it is equal to, we will call it FW, and it is below the centroid of the area outward because of barred H. So we will call that F1, F2, then the distance of F2 from the top is 2/3 of 0.9, 0.6 plus 0.9, so that's why it's 1.5. F1 of course is through the centroid because this is rectangular, so it is 0.9 from the hinge. Then for the force that pushes the vertical side inward, FW, a distance of isa V from the centroid of the area outside, and therefore barred H is H plus 0.9. That's barred H plus 0.9, and call that isa V. So summation moment at the top equals 0. Our working equation to solve for H is FW times this moment arm is 0.9 plus isa V, then equals F1 times 0.9 plus F2 times 1.5, where FW is specific weight of water, barred H, which is H plus 0.9, area of the square, because this is a square, 1.8 by 1.8, 1.8 height, perpendicular to the screen, 1.8, so it is a square. 9.81 quantity H plus 0.9 times 1.8 square. So 9.81 times 1.8 square is 31.784, then quantity H plus 0.9. Then isa V is height of rectangle square over 12 barred H. So 1.8 square over 12 barred H is H plus 0.9. So simplifying the constant, 0.27 over H plus 0.9. That's the value of isa V. Then F1 is volume of this pressure diagram, so 69 times 1.8 times 1.8. So it is 223.56 kilonewtons. F2 is, so we need to solve for P1 yet. P1 is specific weight of water, 9.81 times depth 0.9. So it is 8.829 kilopascals. So therefore F2 is 1 half or 0.5 of 8.829, height 0.9, perpendicular to the board 1.8. So F2 is equal to 7.151 kilonewtons. So we now substitute into this equation 31.784 times h plus 0.9 times quantity 0.9 plus E sub v 0.27 over h plus 0.9 equals F1 223.56 times 0.9 plus 7.151 times 1.5. So 31.784 times 0.9 and quantity h plus 0.9 is 28.606 plus 0.9. 31.784 times quantity h plus 0.9 times 0.27 over h plus 0.9, so cancel h plus 0.9, so we'll have 31.784 times 0.27, which is 8.562. Then the value here combined is 211.93. So we can now compute for h, 211.93 minus 8.562, and the answer divided by 28.606 minus 0.9. So h is 6.209 meters.